let H be Hilbert space. X and Y belong to H. X is perpendicular to Y. The definition of this one is that the inner product of X and Y is equal to what? 0. We have seen the parallelogram law. It says that if you have this kind of element, x plus y norm whole square plus x minus y, this norm whole square. This is 2 times norm of x whole square plus 2 times norm of y whole square. So that is what does it say, is that if you have the parallelogram, suppose this is, let's complete this parallelogram. If you have a vector, suppose this is a vector, this is a vector x, this is a vector y, this is x, this is y, and this is these are the two diagonals over here. So this diagonal is x plus y, and this diagonal is x minus y. This is this diagonal, this is this diagonal, this is x, y, and so on. So the sum of the squares, so what do we have? The sum of the squares, or the length of the square of a length diagonal is sum of square of length of all sides. Now let's come to what is called as a polar identity. So if H is given to be a Hilbert space, then the inner product is related to the norm. So what do we have? First of all, if you take any x and y belonging to H, you know certainly that the norm of x square is an product of x with x. And norm of y square is an product of y with y. What does this say is that 4 times the inner product of x comma y is norm of x plus y whole square minus norm of x minus y whole square plus I times norm of x plus iy whole square x plus iy whole square minus I times norm of x minus iy whole square. And note that what we are talking here, this is Hilbert is our field is a complex field. So f is c. So let's try to prove this thing. This is a complex. For the reals, it is just if f is r, then in this polar identity minus norm of x minus y whole square. So this has a word which is called as polar identity. So let's try to prove. So so the real is easy to prove. So let's try to prove for complex. So the complex Hilbert space. Let's look at RHS of this thing. It is norm of x plus y whole square minus norm of x minus y whole square plus I times norm of x plus iy whole square minus I times norm of x minus iy whole square. This is nothing but inner product of x plus y with x plus y, which is this part, minus inner product of x minus y with x minus y, this part, and then plus I times inner product of x plus iy comma x plus iy, this part, and this is taken here is minus I in the product of x minus iy with x minus iy. So let's open this inner product. What do we get is that this part linearity in the first variable and conjugate linearity in the second. So this is nothing but the first term inner product of x plus y with x plus y. This is nothing but inner product of x with x plus y plus inner product of y with x plus y, and this is nothing but inner product of x with x plus inner product of x with y plus inner product of y with x plus inner product of y with y. This is nothing but norm of x square plus inner product of x with y plus inner product of y with x plus norm of y square. So let's write about x minus y also, what it would be. Inner product of x minus y with x minus y, this would be x inner product with x minus y minus inner product of y with x minus y. Because it is complex linear, conjugate linear, and so it is minus just reals here, scalar x comma x minus inner product with x with y minus inner product with y with x plus inner product with y with y. So this works out to be norm of x square minus inner product with x with y minus inner product with y with x plus norm of y square. So what happens if you subtract this term? So this is nothing but norm of x plus y whole square. This is norm of x minus y whole square. So norm of x plus y whole square minus norm of x minus y whole square. So what happens is that at the same time this term cancels with this thing, this term cancels with this thing. So what happens is that this becomes this thing, so this becomes 2 inner product with x with y, and this minus, this is plus, so this is plus so this minus, if you have with a minus sign, this thing, this, and 2 times. So this is what we have got. Okay. Now let's try to compute the following. So everything is what. So what would happen? So x, just y is replaced with iy. Okay. So what could be said here? Let's write that. First write this term. Norm of x plus y whole square minus norm of x minus y whole square. This is 2 times in a product with x with y plus 2 times in a product with y with x. So let's compute the remaining part. So what do we get? Inner product of x plus iy with x plus iy is inner product of x with x plus iy plus inner product of iy with x plus iy. So this is what inner product of x with x, inner product of x with iy plus inner product of iy with x plus inner product of iy with iy. So what do we get? Is that norm of x whole square. So I is in here, so it's a complex conjugate. So minus I in a product of x with y plus I in a product of y with x. This I is in the first place, so it's linearity in the first variable. So this I comes outside as it is, and this I comes with minus I. So I with minus I, so I into minus I into minus I, norm of y square, which is nothing but norm of x square minus I in a product of x with y plus I in a product of y with x. I square is minus 1, so this is just norm of y square. Okay, so this is what we have got. So let's write this. This is nothing but norm of x plus. Let's rub this part and see x minus iy. What do we get? So let's write it. What do we get? Inner product of x minus iy with x minus iy is inner product of x with x minus iy minus iy into x minus iy. This is nothing but inner product of x with x, and this is the second place, so it becomes outside, so with the conjugate, so plus I minus I conjugate is x plus y minus inner product of I with y comma x, I is in the first place, minus I into this minus minus becomes plus, this I becomes minus I, and then it is in a product of y with y. This is the same thing as norm of x square plus I times in a product of x with y minus I times in a product of y with x. So I square is minus 1 plus, so plus norm of y whole square. This is what norm of x minus iy whole square. Okay. So what's the difference? If you take subtraction of these two things, so norm of x plus iy whole square minus norm of x minus iy whole square. This is what x plus iy whole square minus this, so this term cancels with this thing, same sign, this term cancels with this thing, so this is this thing, so minus 2i in a product of x with y, and this minus this thing, so this becomes plus sign, plus 2i inner product of y with x. So if you take, if you multiply by I, so I times norm of x plus iy whole square minus I times norm of x minus iy whole square. This is what? If you multiply by I square is minus 1. So this is 2 inner product of x with y, and then I square is minus 1 minus 2 inner product of y with x. This with this, if you add, so what would be norm of x plus y whole square minus norm of x minus y whole square plus I times norm of x plus iy whole square minus I times norm of x minus iy whole square. This is what? This is this term added with this term, addition. So this is with a plus sign over here, this term, this is with minus sign. So this two cancel out. So this is 4 times inner product of x with y. That is what we wanted to prove. Okay. The question is that whether the converse is true. So if you have the norm, if you have the Hilbert space and you have a norm, can you produce, say that this is indeed the inner product? So H is already a inner product space. We are having the relation between the norms and the inner product. So if H is a complex Banach space, so on a Banach space, we have a relation that parallelogram is satisfied. So let's try to prove. Then indeed it's a Hilbert space. So let's write the statement first. Okay. The proposition: complex Banach space with parallelogram law is okay with inner product given by x plus y whole square, x minus y whole square, plus I times norm of x plus iy whole square, minus I times norm of x minus iy this square for all x and y is unequal. This is Hilbert space. So let's show that it is indeed the inner product. If we show that inner product, then we are done. It's already a Banach space with respect to the norm. It's a Hilbert space. So we'll use this fact that it's a Banach space and a complex Banach space, and there is a parallelogram law. We first consider the linearity of the inner product of the product, first of all, what is mentioned here with respect to the first variable. Okay. Let's try to show that. Suppose I have x, y, z, any elements of the complex Banach space B with parallelogram law. Consider the following. So suppose we take y and z. Suppose I have the vector, so we'll use repeatedly this identity. For that sake, let's say norm of a plus b whole square plus norm of a minus b whole square is 2 norm of a whole square plus 2 norm of b whole square. Okay. Let a be equal to 2y plus z and b is equal to just z. So what does this become? So this becomes have a different choice for a and b. Let y is equal to maybe say just so what do we have? A and b child and b child. A is equal to z plus y and b is equal to just y. Then a plus b is equal to z plus 2y. A minus b is equal to z simply. Okay. And then we have norm of z plus 2y whole square plus norm of z whole square is equal to 2 times norm of z plus y whole square plus 2 times norm of y whole square. Okay. Now a and b are just any vectors in a in the b. We change this thing. Let a is equal to z minus y and b is equal to y. So if this is the case, then a plus b is what? Is nothing but addition of this thing. So this is z, and a minus b is z minus 2y. So this becomes what? Norm of z minus 2y whole square. Let's write first this term, a plus b is there. No? Norm of z whole square plus norm of z minus 2y whole square, that is equal to 2 times norm of a z minus y whole square plus 2 times norm of y whole square. Then what do we have? We have that. So we'll subtract these two things. So this is true for all y and z. So this term, let's call this equation as 1 and so call this equation, let's number this equation as 1 and this equation this is as 2. Okay. So what do we get? If we subtract them, then 1 minus 2, subtracting the 2 from 1, what do we have? Norm of z plus 2y whole square minus norm of z minus 2y whole square. This is what? 2 times norm of z plus y whole square minus 2 times norm of z minus y whole square. So this is true for all y and z belonging to H. We use this fact. We have just derived this thing from parallelogram law. So let's add a term here. To add and subtract the term and subtract the following object: 2x plus z the whole square. in this equation. So what do we get? Norm of z plus 2y whole square plus norm of 2x plus z whole square minus norm of 2x plus z whole square minus norm of z minus 2y whole square. This is equal to 2 times norm of z plus y whole square minus 2 times norm of z minus y whole square. This could be written as with the minus sign is there, both the signs. So in the bracket, if you want, norm of z plus 2y whole square plus norm of 2x plus z whole square minus norm of 2x plus z whole square plus norm of z minus 2y whole square. This is 2 times norm of z plus y whole square minus norm of z minus y whole square. This is true for all x, y, z belonging to H. We are assuming the parallelogram law. Once we have, so 2 times we have used and subtracted. Now if you look at this object over here, this is there, then what do we get? This is a plus b, a minus b. So let's write maybe. So 2 times norm of x plus z plus y whole square plus 2 times norm of x minus y whole square. This is in fact equal to norm of 2x plus z whole square plus norm of 2y plus z whole square. So you can see that if it is 2a, we call this object. So we consider this object over here, which is what this term. So let a plus b as z plus 2y rather than what we were doing earlier. Let's look at this bottom, what is there, and a minus b as 2x plus z. Then addition of this thing will give you 2a. This addition first. 2a, this is what, 2z plus 2y plus 2x. This implies that a would be z plus y plus x. Okay. The subtraction is what? The subtraction is 2b. So 2b is equal to this minus this. That would be 2y minus 2x. This implies that b would be equal to y minus x. So what we have? So this term would be nothing but this term over here would become what? This would be a plus b norm, a plus b square norm a minus b. So 2 times norm of a square, which is what? Z plus y plus x whole square plus 2 times norm of y minus x whole square. Now we'll just change a b here. So what do we get? So just same thing. So let's call now this is as a plus b as this term. So a plus b is what? Let me say 2x plus z, and a minus b is z minus 2y. So the addition of these two terms would be what? 2z plus 2x minus 2y. 2y, z plus z is 2z, and then 2x is as it is. So a would be z plus x minus y, and 2b would be the subtraction of this thing, so you can subtract also. So if you subtract this thing, so you get 2b is equal to, so z cancels, 2x minus 2y, this would be just x minus y. Okay. So this term over here, this becomes what? This becomes, with a minus sign, 2 times norm of z plus x minus y whole square plus norm of x minus y whole square. Okay. So what do we have over here? This term and this term, so we can write this directly. This term, so 2 times norm of z plus x plus y whole square plus 2 times norm of y minus x whole square minus 2 times, with a minus sign, minus 2 times norm of z plus x minus y whole square, then minus 2 times norm of x minus y whole square. This is this minus this thing, which would be the right RHS of this thing is 2 times norm of z plus y whole square minus norm of z minus y whole square. So of this below part. So we have x plus y terms. Let's see that what is that. Yeah. So this So this is a and this is b. This is assume. So a minus b here would be what? This with the minus sign, this with a plus sign. So this would become x plus y rather. This is x plus y. We will just have a correction over here. This would be x plus y. Here x minus y minus x is correct. So what is it? So let's rub this thing. So what do we have? 2 times norm of z plus x plus y whole square plus 2 times norm of y minus x whole square plus 2 with a minus sign over here minus 2 times norm of z plus x minus y whole square minus 2 times norm of y plus x whole square. This is this RHS, which is this part over here. 2 times norm of z plus y whole square minus 2 times norm of z minus y whole square. Okay. So let's rub the below part. So 2 times norm of z plus x plus y whole square. So we can just divide by 2 or rather 4. So what do we get? Norm of z plus x plus y whole square minus norm of z plus x minus y whole square plus norm of y minus x whole square plus norm with a minus sign whole square is equal to z plus y whole square minus norm of z minus y whole square. Okay. Now this is true for what? All x, y, z belonging to H, or rather B here in this case. If this is the case, then what we can just replace, if B is a complex Banach space, we can replace this B or replace y with iy in this thing. If you replace this thing with iy, what the terms we get over here? So norm of z plus x plus iy whole square minus norm of z plus x minus iy whole square plus norm of iy minus x whole square minus norm of iy plus x whole square. This is equal to norm of z plus iy whole square minus norm of z minus iy whole square. So this term, this is also true for all x, y, z belonging to the complex one-arc space B. If we multiply this with I and so on, so what do we get? Is the term over here. So let's write. So the space is initial. Just a minute. So the below part. So norm of z plus x plus y whole square minus norm of z plus x minus y whole square plus I times norm of z plus x plus iy whole square minus norm of z plus x minus iy whole square plus norm of y minus x whole square minus norm of y minus x whole square, then plus I times norm of iy minus x